Okay, so welcome to another deep dive. Today we are going to jump into a pretty dense survey paper. It's called A Comprehensive Survey of Fuzzy Implication Functions.
Oh yeah, I've seen this one.
And, we always try to pick stuff that's relevant to our listeners, right? And when we talk about fuzzy logic, it can sound a bit like, something out of an old computer science textbook. But this is actually a really important area, especially now with all the advancements in AI and machine learning.
Right, exactly. Because, at the core of fuzzy logic is this idea of dealing with uncertainty. Things aren't just true or false, black or white. There are degrees of truth. And when we're talking about building intelligence systems that need to make decisions in the real world, well, the real world is full of uncertainty.
Yeah, you're not kidding. And that's where this idea of fuzzy implication functions comes in, right? They're kind of like the glue that holds these fuzzy systems together. They allow us to define those if-then relationships, even when we're dealing with those shades of gray instead of just black and white.
Exactly. In classical logic, an implication is very clear-cut. If the premise is true, then the conclusion must also be true for the statement to hold. But if the premise is false, then the whole implication is true by default.
Yeah, that makes sense in that sort of like pure logical world. But like you said, in the real world, things are rarely that clear-cut.
Right. So fuzzy logic steps in and says, okay, let's allow for degrees of truth between 0 and 1. And now the fuzzy implication function becomes this mechanism for processing these degrees of truth in those if-then rules. So it's really at the heart of how these fuzzy systems reason and make inferences.
So this survey paper, it's not like introducing some brand new groundbreaking theory, right? It's more like a taking stock of where we are in the field of fuzzy implication functions. Why did the authors feel like this was necessary? Why now?
Yeah, that's a good question. And you hit the nail on the head. It's about taking stock. So the thing is, over the last decade, there's been an explosion of research in fuzzy implication functions. Researchers have been proposing all these new families of these functions, each with their own unique properties and ways of working. And that's great. It shows the field is active. But it's also created this kind of overwhelming landscape.
Right. So many options. How do you even know where to start?
Exactly. It's become really difficult to keep track of what's out there, to understand how all these different approaches relate to each other, and most importantly, to know which fuzzy implication function is the right tool for a particular job. And that's really the problem this survey is trying to address. It's trying to bring some order to this chaos to provide a roadmap for both researchers and practitioners.
Okay, so that's the motivation. So what exactly does this survey do to kind of make sense of all this?
So it takes a very structured approach. It walks us through the different families of fuzzy implication functions, explaining their motivations, their mathematical properties, and even pointing towards potential applications. It's really trying to be this comprehensive resource for anyone working with fuzzy logic.
So both for the people who are developing the theory and the people who are actually using it in practice.
Exactly. And one of the key things the survey emphasizes is this idea of characterization, really understanding the specific features of each family, what makes them tick, what properties they guarantee, how they compare to others. And they even use these really helpful schematic diagrams to visualize these relationships. It makes it much easier to grasp this pretty complex information.
Okay, so that's super useful. Now, we know that fuzzy implication functions generally kind of, decrease in their first argument, the premise, and increase in their second, the conclusion. But the paper also talks about these additional properties. What are those all about?
Yeah, those are really important because that's where we start to see the subtle but really significant differences between all these different fuzzy implication functions. It's where we get into the specifics of how they behave logically.
Okay.
I'm intrigued.
So you can think of these additional properties as like specific logical axioms or behaviors that a particular fuzzy implication function might satisfy. Many of them are actually extensions of fundamental logical truths that we see in classical logic.
Oh, okay. So they're kind of like taking those classical ideas and adapting them to this world of fuzzy logic.
Exactly. So for example, you have the identity principle, or IP, which basically says that something fully implies itself. It sounds obvious, but it's a key property for ensuring consistency in fuzzy reasoning.
Okay, yeah, that makes sense. And what about some other examples?
So there's the exchange principle, EP, which is about the order of premises in a nested implication. It says that the order shouldn't change the overall meaning. And then you have things like the ordering property, OP, which links the degree of implication to the ordering of the truth values. Basically, a higher degree of truth in the premise should imply a lower or equal degree of truth in the conclusion for the implication to be fully true.
Right. So it's like establishing that cause and effect relationship even in this fuzzy world.
Exactly. And then there are properties that relate to how these functions work in fuzzy inference systems, like the left neutrality property NP, which says that if the premise is completely true with a truth value of 1, then the truth value of the implication is just the truth value of the conclusion. It simplifies things.
Okay, I can see how that would be useful. And are there any that are specifically relevant for like building those chains of logical reasoning that you often need in AI systems?
Oh, absolutely. So there's contrapositive symmetry, CPN, which is the fuzzy version of the idea that if P then Q is equivalent to if not Q then not P. It's crucial for certain types of logical deduction. And then you have T-conditionality, TC, which is all about generalizing the classical idea of modus ponens. If we know P is true to a certain degree and P implies Q is also true to a certain degree, then TC helps us determine the degree to which we can infer that Q is true.
Right. It's like the building block of that if-then reasoning.
Exactly. And for those longer chains of reasoning, we have the generalized hypothetical syllogism, GHS, which basically extends the transitivity of implication.
Right.
So if P implies Q and Q implies R, then GHS tells us something about how strongly we can say that P implies R.
Got it. So all these properties are like giving us this toolkit for really fine-tuning how our fuzzy system reasons.
Exactly.
Hello.
And the survey paper goes into detail about a whole bunch of them. It's a really comprehensive resource for understanding how these different properties can be used to characterize and select the right fuzzy implication function for a specific task. Yeah.
Okay, so we've got a good handle on the properties. Now let's talk about how these different families of fuzzy implication functions are actually constructed. The paper outlines 4 main strategies.
Right, and it's a really good way to organize this whole landscape. So the first strategy, and probably the most common, is to generate new fuzzy implications from other existing fuzzy operators. So we're talking about things like T-norms, which are like fuzzy AND operators, T-conorms, fuzzy OR, and fuzzy negations.
Okay, so you're taking these basic building blocks of fuzzy logic and combining them in specific ways.
Exactly, and the formulas for doing this can get pretty complex. But the goal is to create a new function that behaves like a fuzzy implication, satisfying those core properties, like decreasing in the first argument and increasing in the second, and hopefully some of those additional properties as well.
So you're kind of engineering these functions to have the specific logical behaviors you want.
Right. And a lot of the really foundational families of fuzzy implication functions fall into this category, like the SN implications, which are based on that classical idea of material implication, not P or Q. And the R implications, which are derived from this concept called residuation. It's a way of defining implication based on a T-norm.
Okay, and I'm guessing there are variations within those broader categories.
Oh, yeah, definitely.
Yeah.
So you have implications that are generated specifically from fuzzy negations, and you have generalizations that use more sophisticated ways of combining truth values, like norms and disjunctors. It's a very rich area.
So that's the first strategy. What about the other 3?
So the second one is about generating fuzzy implications from n-ary functions. These are functions that take a single truth value as input and transform it in some way.
Okay, so they're operating on individual truth values rather than combining them.
Exactly. And one famous example of this is Jaeger's F and G implications. They use these mathematical generators to define the implication. It's a pretty elegant approach.
Interesting. And what about the third strategy?
So the third one is about taking existing fuzzy implication functions and modifying them to create new ones. It's like you're taking a function that already works and tweaking it to get something with slightly different properties or behavior.
So like fine-tuning it.
Yeah, exactly. And there are various techniques for doing this, like contrapositivization, which involves applying a fuzzy negation to the inputs, or taking weighted averages of different implications, or using these more complex methods like ordinal sums, which allow you to piece together simpler implications defined on different parts of the truth value scale.
Okay, so it's getting pretty sophisticated. And what's the final strategy?
The fourth one is a bit more recent, and it's about constructing fuzzy implications directly based on their final mathematical formula. So instead of starting with other operators or existing implications, you just define the function based on the desired mathematical expression.
So it's a more direct approach.
Exactly. And one example of this is fuzzy polynomial and rational implications, where the function is defined by a polynomial equation, or ratio polynomials. This approach is often driven by wanting specific computational properties or making the function easier to analyze mathematically.
Okay, so it sounds like there's a lot of flexibility and creativity in how these different families are constructed. Now, thinking about our focus on machine learning, can you highlight a few families that have been particularly impactful in that field?
Oh, yeah, for sure. So fuzzy rule-based systems are a big area in machine learning, especially when it comes to interpretability. And the choice of fuzzy implication function is absolutely crucial in these systems. It directly affects how the system reasons with uncertain information and makes decisions.
So it's not just a theoretical exercise. It really impacts the practical performance of these systems.
Exactly. So one family that's particularly important are the R implications. They have this really strong connection to mathematical structures called residuated lattices, which have been studied extensively in logic and AI, and they often have properties that ensure a good degree of logical coherence in fuzzy reasoning.
Okay, that makes sense. And what about other influential families?
So SN implications are very popular because they're so flexible. Since they're built using a T-norm and a T-conorm, you have a lot of freedom to choose those operators, which can lead to a wide range of different implication behaviors.
Right, so you can tailor them to the specific needs of your application.
Exactly. And the paper also talks about implications derived from copulae, which is interesting because copulae are also used in probabilistic modeling to understand relationships between random variables. So this connection could be really useful for bridging the gap between fuzzy logic and probabilistic approaches to uncertainty in machine learning.
Yeah, that's a really interesting connection. And it sounds like there's still a lot of research to be done in understanding how these different families perform in different machine learning contexts.
Definitely. I mean, the goal is to avoid just having this huge collection of functions without really knowing which ones are truly novel and effective for different tasks. The research highlighted in the survey is all about characterizing these families and identifying their strengths and weaknesses in areas like fuzzy control decision-making, data mining.
Okay, that's super important work. So this brings us to our novel notions segment, where we kind of like to speculate a little bit about potential research directions that the survey might inspire. And, given this massive, almost overwhelming landscape of fuzzy implication functions, what are some areas that you think are ripe for exploration?
One thing that really jumps out at me is this idea of context-aware fuzzy implication selection. I mean, the survey makes it so clear that there's no single best fuzzy implication function for every situation. It really depends on the specific problem, the data, the type of reasoning you need.
Right, so it's all about choosing the right tool for the job.
Exactly. So the novel notion here is to develop these meta-learning frameworks that can automatically select or even intelligently synthesize the most appropriate fuzzy implication function from this vast library that we now have.
So it's like having an AI system that can adapt its own logic based on the context.
Precisely. Imagine a medical diagnosis system. It might reason differently about the relationship between a mild symptom and a potential condition compared to a more severe symptom. This framework could learn to choose or even create the ideal fuzzy implication for each specific diagnostic rule within the system.
That's a pretty powerful idea. And I'm guessing the survey kind of lays the groundwork for this kind of research.
Oh, absolutely. By showcasing this incredible diversity of families and properties, it really highlights the need for this kind of context-aware approach. And we can even draw inspiration from recent advancements in things like AutoML and neural architecture search to develop these algorithms for exploring the space of fuzzy implications.
So it's like taking those techniques that have been so successful in other areas of machine learning and applying them to this problem of fuzzy implication selection.
Exactly. And the potential impact here is huge. I mean, it could lead to much more accurate, robust, and interpretable fuzzy machine learning systems. And that could translate into breakthroughs in areas like personalized medicine, adaptive control, and even risk assessment.
Okay, that's super exciting. What about another research direction?
Another really interesting avenue to explore is hybrid fuzzy neural inference with learnable implications. So we know that fuzzy logic is great for interpretability and handling symbolic knowledge, while neural networks are awesome at learning from data.
Right, they both have their strengths.
Exactly. So the idea here is to create these hybrid systems where the fuzzy implication function itself isn't fixed, but actually becomes a learnable parameter or even a small neural network within the overall architecture.
So instead of us having to choose the implication function beforehand, the system could actually learn the best one from the data.
Exactly. Imagine an autonomous driving system. You might have fuzzy rules based on expert knowledge about safe driving, but the exact way those rules are applied through the implication function could be fine-tuned based on the massive amounts of real-world driving data that the system collects.
So it's like combining the best of both worlds, the interpretability of fuzzy logic with the learning power of neural networks.
Right. And this could lead to much more adaptable and robust AI systems. I mean, think about robots that can actually learn from experience or decision support systems that can handle much more complex scenarios.
These are some really fascinating and potentially groundbreaking ideas. And it's amazing to see how this deep dive into a seemingly theoretical topic like fuzzy implication functions can actually spark such practical and impactful research directions in machine learning.
Absolutely. And just to emphasize, that these novel notions are really just meant to be starting points to get people thinking about the possibilities. There's so much more to explore in this area.
Yeah, for sure. So to wrap things up, I think the key takeaway here is that the world of fuzzy implication functions is incredibly rich and diverse, and it offers this amazing toolkit for tackling the challenges of uncertainty, which is so crucial in machine learning. And this survey paper is an invaluable resource for anyone who wants to delve deeper into this field.
Yeah, I highly recommend checking it out. It really lays the foundation for understanding this complex but fascinating landscape. And as always, we'll include the link in the show notes.
Absolutely. And I think it leaves us with this really thought-provoking question. As we build more and more AI systems that are integrated into our lives, how will the choices we make about the very logic that governs them, choices like selecting or even learning fuzzy implication functions, ultimately shape their behavior? And more importantly, how will those choices influence the trust we place in them? It's something to really ponder as we move forward in this age of intelligent machines.
It really is. It's not just about the technical details. It's about the fundamental principles that guide how these systems reason and interact with the world.
Exactly. It's something we need to be thinking about carefully.
Absolutely.
All right. Well, that was a really insightful deep dive. I think we covered a lot of ground.
Yeah, I agree. It's a complex topic,
Yeah.
but hopefully we've shed some light on the key concepts and the exciting possibilities.
Definitely. And thanks everyone for listening. We'll be back soon with another deep dive into the world of machine learning research.
Looking forward to it.